Hey, so here we are at the review stations. And I'm just wondering because for some reason I don't have station one. I'm sort of wondering what it is. It's in the classroom, but I'm not there. So, this set of review stations starts with station two. Okay, problem one. W prime is the rate at which a child gains weight. Um, Means weight and in pounds per year. Okay, so part A, what does the integral from 5 to 10 of w prime t dt mean? Well, this is our rate, pounds per year, and this is our time. And so this is going to give me the change in the child's weight from age 5 to age 10. And I guess I want to say, I could probably get the credit for that, but I want the net change. So, if this child gains weight and then loses some weight and gains some weight, this is the net change in weight. Okay, part B. How much does the child weigh at age 5? If the integral from 5 to 10 of w prime dt is 45, then the integral, that's a typo. That shouldn't be integral. It should be and w of 10 equals 80. So maybe I can get that changed. Station 2. All right. So we know this information, we know this information, and we want to know the child's weight at 5. So, think about FTC2. If you integrate from 5 to 10 w prime, that's going to be w of 10 minus w of 5. So, if I'm looking for w of 5, I want to subtract w. I'm going to add this and subtract that. So, I'm now going to have w of 5 equals w of 10 minus the integral from 5 to 10 w prime dt. Well, conveniently, they give us some values here. This is 80 pounds. This is 45 pounds. And so we get 35 pounds is w of 5. So the child weighs 35 pounds when they're a 5-year-old and 80 pounds when they are a 10-year-old. Okay. 2. A honeybee hive starts with 100 bees and increases at a rate of n prime equals bees per week. What does the integral from 0 to 15 of n prime dt plus 100 equal? Well, what I think that, honeybee hive starts with n of 0 equals 100 bees. Okay, so we've got a starting amount, we've got a rate, and we want to know what's up with this. Well, I think I'm really just looking at that FTC2 thing again. I think I'm looking at n of 15 minus n of 0 equals the integral from 0 to 15 of n dt. And if I add n of 0 to both sides, which is the same as adding 100 to both sides, that's giving me exactly what they're looking for, which is n of 15. And so what am I finding there? I'm finding the number of bees in the hive after 15 weeks. Okay. Yeah, and we can't actually find a value for that because there's no, there's no, just no. There's no function, there's no way to figure out what n prime is here. We're not provided with the integral of n prime, so yeah, that's as far as I can go. Question 3, a storage tank has 50 liters in it. When water starts flowing in at a rate of 200 minus 4t, and those are in liters per minute. All right, so I think I can say the integral from 0 to 50 of r dt equals the amount at 50 minus the amount at 0. And what do we know? Well, we know that this is 0 to 50 of 200 minus 4t. And over here, we've got a of 50, and we know a of 0 is 50. They tell us at time equals 0, there are 50 liters present. Don't confuse these minutes with these liters, okay? So what are we asked? How much water flowed into the tank during the first 50 minutes? Okay, so that is just this part. If we want to know what flowed in, we're just going to evaluate this integral. And so we're going to have 200t minus 2t squared from 0 to 50. Okay, I plug in a 50, and I get 1, 2, 3, 4 zeros, minus 50 squared is 65,000. 50 squared, 6,500, I guess I would have said. 2,500, yeah, it's good to check those things, times 2. So we're subtracting 5,000. And just to be sure, 20 times 50, yes, 10,000. Okay, so we know that 5,000 flowed in on 0 to 50 minutes. And these are liters? Liters. Okay. That's part A. But now part B, how many liters are in the tank after 50 minutes? So that's this FTC thing, right? Where they're asking me for what's the amount at time equal to 50. We know the amount at 0 is 50. And now we just evaluated this integral. We got 5,000. So I'm going to put a 5,000 on this end. And I'm going to say, well, A of 50 is simply going to be A of 50 is 50 liters. Okay. Nice. That was station 2. Let's take a look at station 3. Station 3 says, what is the average value of this function? Station 3. Okay, y equals 3t to the third minus t squared on negative 1 to 2. Okay, so I remember the average value formula as being 1 over b minus a, integral a to b of 3t to the third minus t squared dt. And we have our a and our b over here. So let's plug some things in. We're going to have 1 over 2 minus 1, integral negative 1 to 2. Integral here is going to be t to the fourth, 4 minus t to the third over 3. Now this is just so wrong, because I'm doing the antiderivative with the integral sign still there. So I'm going to do it as 2 separate steps, just like Leibniz intended and the College Board would like to see. And so this is going to be 1/3. Now I'm going to do the antiderivative and say that'll be 3/4 to the fourth minus 2 to the third over 3. And I would like to evaluate that from -1 to 2. Okay, so if I plug a 2 in here, 2 to the fourth is 16, divided by 4 is 4, 4 times 3 is 12, minus 2 to the third is 8, so I get 8/3. And then I'm going to plug in the -1, so this is going to be 3/4 minus 1/3. Alright, so that's 36/3 minus 8/3. I think that's 28/3. Yes, that's 36. And here, 12ths. So 9/12 minus 4/12 is 8/12. 32, 112 minus 8, 104 over 12. And I guess that could be reduced. I could certainly take a 2 out of there. Maybe I could even take a 4 out of there. But instead, I'm going to stop. Oh, look. It's multiple choice. I guess I do need to keep going. So this will be 52 over 6 and 26 over 3. I don't see 26 over 3. Oh, that's very sad. Okay, so let's plug 2/4 to the fourth, 2 to the third over 3, -1. Ooh, -1. I blew it with the sign. So let's see about that again. There's a 1/3 16 divided by 4 is 4, times 3 is 12, minus 8/3. Minus, now to plug in the -1. That's going to be a positive 3/4, but -1 times -1 times -1, -1/3 times a negative is plus 1/3. Okay, so if I make a common denominator here, I have 9 plus 4, which is 13/3. Okay, so we're going to have 1/3. We're going to have 36/3 minus 8/3. And this is minus 13/3. I think that's correct. So this is going to be 23. It's 21. That's 15/3, 15/9. I can take a 3 out of those and get 5/3. And I don't see that one either. Bah! Come on, trusty calculator. Help me out. Okay. We want 1 divided by 3. Math, integral 3x to the third minus x squared, x, -1, 2. Fraction. We see 11/4, and that's choice A. So let's see where I'm making that bonehead mistake. I still like that integral. Because the 4 would come down and cancel. Minus the 3 would come down and cancel. Give me that. So I like that. Okay. That's not what the issue is. So this is definitely 1/3. I plug in my 2. 2 times 2 times 2 times 2 is 16. Divided by 4 is 4 times 3 is 12. Next, plug in a 2 here. 2 times 2 times 2 is 8 over 3. Well, that stayed the same. Minus. Now I'm plugging in my -1. -1 times -1 times -1 times -1. 4 -1s is going to be +1 times 3/4. And then minus, plug in a negative 1 here. Negative 1 times negative 1 times negative 1 is negative 1/3 behind this minus. So we're going to have plus 1/3. Okay, so we can make a common denominator. Yep, I'm so close to the right answer, but really not close enough. That's 9. That's 4. 9 and 4 is 13. So that's minus 13/12. That was the last mistake. And then over here, we have 36 thirds minus 8 thirds is going to be 28 thirds. So 28 thirds minus 13/12. And by that, and don't forget the 1/3 out front. So now you have 4 over 4. Okay, so now I've got 12s. I believe that's 112 tenths minus 13/12. Let's check. 28 times 4. Minus 13. Yep. So this becomes 99/12. Okay. A 3 there. 3/12. Another 3. And there we go, 11/4. And that's A. Watch out for those small mistakes. Yeah, every time. All right, question 2 on station 3. The area bounded by x equals 3y minus y to the second on, and the line negative y equals x. Okay, so let's graph these. This factors as 3 minus y and y. So we've got 3, 0, and parabola has a negative leading coefficient, and so there's the graph of this. See the negative y squared? That's where y squared goes. This would be up if I look sideways. This is down if I look sideways. So my y, negative y squared looks like that. Now over here we have x equals negative y. So there's x equals negative y. And I guess there's some point of intersection over here. I wonder when these two intersect. Well, they're both equal to x, so I can set them equal to each other. Y minus y squared. Please do not subtract this from both sides. Please put all the y's on one side. 4y minus y squared. And then we can factor out a y. We can see that there are intercepts when y is equal to 0, but also here when y is equal to 4. Remember, negative y equals x. So 4, negative 4 equals x. All right, what are we doing here? We're finding the area of this region. Well, again, I don't want to do top minus bottom because, well, that would work fine over here. You get over here and the top and the bottom are treated, they're the same function. And so I literally have to try and figure out where this line is and split this into two integrals, one that goes from here to here, and another one that goes from here to here, and that sounds insanely crazy. Don't do that. Instead, just do right minus left. Sometimes right minus left is the perfect thing to do, and that's what we've got here. There's our downturned parabola, and that's this one here, 3y minus y squared. And that's my right. Now my left is this one, which is minus the negative y to y. You see enough of these y's? So we're integrating y's, not from here to here, but from here to here. We're going from 0 to 4. Okay, so we've got 4y minus y squared 2y from 0 to 4. My antiderivative then will be 2y squared minus y to the third over 3 from 0 to 4. I plug my 4 in, and I get 16 times 2, or 32. I plug my 4 in, and I get 4 to the third, which is 64 over 3. I'd like a common denominator here, so I'm going to have 96 minus 64 over 3. And that turns out to be 32 over 3. All right, there's my area. Any questions about that? Nice. Okay, that was station 3. Station 4. Graph of velocity is given. Okay, velocity graph. And we go uppity up, up, down, down, down. And that's 3, and that's 2, and that's 1. And then we've got this horizontal space until we get to 6. And then there's 7, there's 8, and then that's an 8, not a 9. And over here for 10. These are seconds, and this is meters per second, so this is a velocity graph. Find where the particle is at the end of the trip. Oh, in the stem of the particle, they say starts at x equals 2 when time equals 0. So x of 0 equals 2. Okay. Where are we at the end of the 10-second trip? So we're trying to find x of 10. Well, I know that x of 10 minus x of 0 will equal the integral from 0 to 10 of v of t dt. All right, so if I'm looking for x of 10, that just means I have to add x of 0 to both sides. v of t dt. Excellent. 2 goes in here. Now what about this integral? Well, this is a triangle. The height of this triangle is e. Same thing over here, 3. Okay. And so we know the base is 2 and the height is 3. We're going to have 1/2 2 times 3 plus. Now we have this trapezoid here, and that's going to be 1/2 times the height. The height there is also 3, but notice this is down 3. It's a minus 3. And base 1 goes from 2 to 7, plus base 2, which goes from 3 to 6. Okay, and that minus is terribly, terribly important, because we're going to have to take this amount away from those. But wait, there's one more triangle. It has a base of 3 and a height of 3. So we'll have 3 times 3. And I could actually leave my answer like this for the AP exam, but I just can't. And then we're asked to find the total distance traveled. Okay, so let's see what we know. We know that this is going to be 2 plus 3 plus 8 divided by 2 is 4. 4 times negative 3 is negative 12. And plus, this is a 1/2, 9/2. Okay, so this is finding us x of 10. So that's 5 plus 4.5 is 9.5. From 9 to 12 is 3. So this must be 2.5. Negative 2.5 or negative 5. We had minus 12 plus 4.5, 9.5, which is 19/2. So 24/2 minus 19/2, that's going to be minus 5/2. Good. Okay, now the reason I wanted to write this out is because this next question says, what's the total distance traveled? The total distance traveled is this 3 plus 12 plus 9/2. And so that's 15 plus 4.5. 19.5 or 39/2. Okay. Just made a common denominator and added them together. And remember, all the stuff below that time axis Yeah, that area has to be turned positive for total distance, right? When I'm doing FTC part 2, no, that stuff below stays negative. But when I'm doing total distance or integrating the speed function, in these cases, I want to add all the positive values, and that means I need to make that positive. All right, that was station 4. Oh, no, it wasn't. That was only the first part. The half-life of cesium-137. Cesium-137 is 30 years. We have Q sub O 1000 milligrams. Find the mass that remains after T years. Well, they want me to write a model. So Q equals 100, not 1000. E to the ln of a half over 30 T, right? That's our shortcut for K in half-life problems. So there's part A. Part B, how much remains after 100 years? So we want Q of 100, E half over 30 times 100 years. Well, let's pull out that calculator and find out. We've got ln of a half divided by 30 times 100, and we want e raised to that power. Then don't forget to multiply that number times 100. Well, I end up with Q of 100 as being 9.921 milligrams after 100 years. Okay, and how long until only 1 milligram remains? Well, 1 equals 100 e to the ln of a half over 30 t. I'm solving for t. So I'm going to divide by 100. I'm going to take the ln of both sides. I'm going to flip and multiply. So that's going to be 1 over 100, or better yet, 0.01 equals e to the ln of a half over 30t. I want to take the ln of both sides now. And bring this down. Oops, bring all of that down. And then to wrap it up, I'm going to multiply by 30 over ln of a half. Perfect. Okay, so ln 0.01 divided by ln of 0.5. I want that times 30. I get 199.316 years. Okay. Now that was station 3. No, 4. Station 4 is done. Let's take a look at station 5. There are, I believe, 12 stations here. All right, 5. Sarah's velocity is given by g squared. No, t to the 1/2. Thank you very much. Minus 2, and these are measured in feet per second. When would her velocity be 0? All right, 0 equals t to the 1/2 minus 2. 2 equals t to the 1/2. Raise both sides to the 2 over 1 power. So we get t equals 4. I squared both sides. So this is a must check, but when I think about squaring both sides, there's no reason this shouldn't be fine. When would her velocity be 0? When t equals 4, v of t equals 0. There's part A. Part B, find the net displacement on 1 to 9 seconds. Well, we know that displacement, even more emphatic net displacement, is x of 9 minus x of 1. So that's going to be the integral from 1 to 9 of v dt. 1 to 9. Now, do we know position at 1? I don't. know that. Okay, so I know I don't need to find that because I'm looking for displacement. I'm looking for this minus this. That is the displacement. Okay, so antiderivative. Okay, and the antiderivative of this velocity function, 2/3 t to the 3/2 minus 2t. And we're going from 1 to 9. Now, you see this 3/2? Yeah, that's why we have 1 and 9, because I can take the square root of these numbers. So when I plug in a 9 here, square root of 9 is 3, 9 times 3 is 27, 27 divided by 3 is 9, times 2 is 18, minus 2 times 9, which is 18. Now let's plug in a 1. 1 to the 3/2 is 1, times 2/3, minus 1 times 2 is 2. So this is 2 minus 6/3, so I end up with minus a minus 4/3, or positive 4/3. And that's her net displacement. Net displacement 1 to 9 seconds. I think these are feet. So I'm going to put some minutes. All right, total distance traveled on the same interval. Well, come on, you see the word total. That means two integrals. Square root of t minus 2. Okay, so 0, -2. Where's that point? Well, that's 4. How do I know? That's when the velocity equals 0. So if I put my 0 here, I have to add 2 and then square both sides. 2 squared gives me 4. And we're going from 1 to 9. Okay. And here we want the total distance traveled. Well, instead of going with just the plain old integral from 1 to 4 of v of t dt, I'm going to say negative. Why? Because if I just do this integral, that integral is going to be equal to some negative number. But if we're looking for total distance traveled, that needs to be a positive number. So if the integral is negative times a negative, that will give me that positive. And then I want to add the integral from 4 to 9 of v of t dt. Okay? All right, so let's figure out what that value would be. We know our antiderivative here is 2 to the 3/2, 2/3 in front, minus 2t. And we want to go from 1 to 4. So if I plug in a 4, square root of 4 is 2, 2/3 is 8, I have 16/3 minus 8, which is 24/3, minus, now I'm plugging in a 1. So I'm going to get 2/3 minus 2. 2 is 6/3. Okay, that's going to be negative 4/3. Minus is plus 4/3. And over here, 16 minus 24 is negative 8/3. And so when I add those together, I have negative 4/3 with a negative. So this is 4/3. And what about from 4 to 1? Okay, well, this is 4. 4 to 9, rather. Okay, so if I plug that 9 in, square root of 9 is 3, 3 to the 3rd is 27, 27 divided by 3 is 9, 9 times 2 is 18. So I've got 18, and 2 times 9 is 18. Good. And I'm subtracting from that this value at 4. This value at 4 was 16/3 minus 2 times 4 is 8, so 24/3. Okay. So 16/3 minus 24/3. So that's 0. And that's negative 8/3 times a negative is positive 8/3. And this is time. How far does she travel? And these are in feet. 129 seconds. Okay, here's station 5, number 2. Station 6. The humor starts at 7 a.m. T equals 0. Now T equals 1, which is 8 a.m. 20 people know it. So R of 1 equals 20. I guess R of 0. Well, is that 1 people or 2 people know it? And then what do we have? You know that the rate of change in the number of people who know this thing with respect to time is proportional to how many people know the rumor. So here, they give me the differential equation. I need to solve that differential equation. Don't forget the separation of variables and the integrating. And P equals KT plus C. Exponentiate absolute P equals e to the C times e to the KT. P equals plus or minus e to the C times e to the KT. If we say that plus or minus e to the C is B, then I can come back over here and say that P equals B e to the KT. All right, so we know the original amount. If we plug in a 0, we get 2. So 2 equals B e to the 0. E to the 0 is 1. 1 times B is B, so B must be equal to 2. And now let's plug in this other point. At time equal to 1, P is 20. So 20 P prime. That's what that should be called. Okay, if I plug in my 20 for P, no, that's P of 1 is 20. And P of 0 is 2. These aren't P primes. Sorry about that. Okay, 20 equals 2e to the 1 times k. Okay, so 10 equals e k. Ln of 10 equals k. That's the model. Okay, I've got a model, and we want to know when the model equals 1,000. So again, that model is P equals 2e to the ln of 10 times 2. I believe that to be correct. Okay, so, yeah, because 1 times k is k. And we know that P is 1,000 people. So, ln of 10. And we want to, I guess I'm solving for that. So really I want to start by dividing by 2. 500 equals e to the ln 10 t. So now I take the ln of both sides and divide by ln of 10. ln of 500 divided by we get t equals 2.6989. Or 2.899. I'm sorry, 2.699. All right, and those would be measured in hours. Wow, after After 1 hour, there were 20. After 2.699 hours, there are going to be 1,000 people in the rumor. That's pretty scary. Okay, next question. It says, World Wildlife Federation has estimated that there are 3,200 tigers, only 3,200 in 2010. Okay. Now, we've got, and in 2016, 2 6, we've got 3,890 tigers in the wild on the planet. And that's the whole planet. There are only this many in the wild. There's, I wonder how many there are in zoos. I wonder if we have more tigers in the zoo than we do roaming the planet. That'd be kind of sad. But humans are going to like that. We like to be the alpha predator. Okay. Oh, isn't that interesting? The rate of change in the population with respect to time is negative 0.000114p and 6,400 minus b. And if we solve that differential equation, and no, I'm not asking you to, but I did, we end up with p of t is 6,400, 1 plus e to the minus 0.073t. There's our logistic curve. Okay, what is the maximum estimated size of the tiger population according to this model? Well, that's it. I mean, if I put in a really big number here, like 100 trillion, or a trillion, even if I multiply it by this, yeah, so it's be a trillion. So I have e raised to the negative trillion power. Yeah, if you've got only one pizza and e to the trillion people coming over, I'm going to say that, yeah, that's 0. You don't get any pizza. Plus 1 is 1, and 6,400 divided by 1 is 6,400. So part A, we're looking for p of 0, and I get p of 0 to be 6,400. Okay, part B, find p of 6. Is the population above an accurate, is the population model above accurate based on what you know in this problem? Oh, well, we were told that time equal to 6, there were this many. So now they want me to plug time equal to 6 in here and compare this result with the actual result. Okay, so 0.073 times 6, and I want e raised to that power plus 1, and I'm going to take 6,400 and divide by that last answer. And I get that the p of 6 equals 2510.193 times. The old-time spelling of tigers. All right, so, yeah, so no. This model predicts a much lower number of tigers at 2016. That's not p of 0. That's p of infinity. That's the population we're headed towards. Okay, I wonder what p of 0 is. I'll plug a 0 in here. P of 0 is 1. Oh yeah, no. I get 1 plus 1, which is 2. So 6,400 divided by 2 is 34. But why did this go down? This shouldn't go down like that. Let me check my answer again. Okay, so we have negative 0.073 times 6. All right, and I want e raised to that power. Good. Is there a number here in front? There's none. Plus 1. And I want 6,400 divided by that answer. And that's a different number. That number is 3889.807. All right, and damn, not bad, little model. Good job. Okay. How many tigers are there when the tiger population is increasing fastest? Use dp/dt to justify your claim. What is this rate of change? And don't forget to include units. Well, that's very interesting. So here's what we remember, or are supposed to remember. That's y equals 0. Here's our y equals 6,400. And here is our time axis. And this is t equals 0. And that's 0, 3,200. Okay, but what do we know? Well, what we know is the rate of change in p. This logistic curve here is p. The rate of change in p, the slopes on p. I see positive slopes everywhere. But where are the slopes on p greatest? Well, I see the greatest slope. Yeah, I'm not sure. I think it's around here. Maybe it's even here. Well, in August, we learned that the rate of change will always be greatest at the output value of this divided by 2. And that's this line here, 3,200, which in fact occurs at t equal to 0. Okay, so they want us to determine the rate, and we're using dp/dt. Okay, so here's my dp/dt. I'm going to plug in this population here and here. What do I get? 6,400 minus 3,200 is 3,200. And then 3,200 times negative 0.1234114. Okay, and I'm multiplying that times the 3,200 here. And I get p prime of 0 is, what? No, that can't be. That's not right at all. Because this always has a positive slope. That's so interestingly weird. Huh. Well, that's very, very interesting. Okay. So, so let's 6,400 minus 3,200. Just recalculated that. That's a negative. That's a positive. I get dp/dt equals negative. And dp/dt can't be negative at that point. You know, I think I've screwed up somewhere in these two. Yeah. That's going to be positive p squared minus p. Yeah. I think that's got to go. Let's try the problem that way. Okay, so I've got 0.0000114 times 3200 times 3200. Yeah, that fixes it. So I know that this number is supposed to be 116.736. And what are the units on that? Well, that's very interesting. Let's do PDT. These are still in years, and these are tigers. But this is P times P for P squared, so no. Okay, so this is change in population, tigers over change in time, year. All right, population is going up by 116.736. That's the rate at this time. And what was the time? How many tigers are there when the population is increasing fastest? So there are 3,200 tigers. Population grows fastest. Okay, and there's two ways we could do this. One was that sort of pre-cal approach, where we know that this steepest place, this occurs at, sorry, I just want to make a note to change this differential equation, station 6. And we want to get rid of that negative. Okay. So that's when the population grows fastest. And we use that sort of carrying capacity, that L, to do L over 2 here. We don't know the time in this problem. It turns out to be 0. We could also, though, since this is the inflection point, we could pull out our calculator. We know this is a calculator question. We pull out our calculator and do P of t in y1, P prime in y2, P double prime in y3, and look for this x-intercept in y sub 3. Okay. And then once we find that value of the x-intercept on P double prime, we can take that time and plug that time back into P just to get that 3,200. That seems like a lot of work. Okay, and then what is the rate of change in population? There's the rate of change in population. And we included units. Okay. Station 7. Oh no, that was station 6. Station 7. Oh, what? There's more? This is very confusing. These look like stations I started but didn't finish. Well, that's going to be interesting. So I guess this one is now called Station 7. And this one's going to be Station 8. Okay, consider, this is Station 7. Consider f of x equals e to the minus x squared, x equals 0, and x equals 1/2. Okay, so this, by the way, is that bell curve. And we're going from 0 to 1/2, and we're bounded here. This is what we're talking about. Estimate the total area bounded by, a second. Okay. Estimate the area of this region by using a left Riemann sum. Let's change that to left Riemann sum. 57 intervals. No, way. Because you don't have that program in your calculator. Left sum with 4 subintervals. Now, if we had a calculator program, I feel comfortable with 50. I'm going to go with 4. Okay, so, and then is this estimate an upper or lower bound for the actual area? Well, remember, if we're doing LRAM, we're going to the left side of the interval, going up until the curve, and then coming back across. So even though I've only drawn one subinterval there, I see that LRAM in this situation is going to be an overestimate. Now, remember, decreasing functions. Doesn't matter if I'm concave up, decreasing functions overestimate, or if I'm concave down, decreasing function is an overestimate. Okay, so decreasing for LRAM is an overestimate. And what do we need to do? We need to find 4 subintervals on 0 to 1/2. Oh, just sounds painful. So 1/2 minus 0 divided by 4 is 1/8. Okay, so I'm going to have some values on the table. I'm going to have 0, 1/8, 2/8, 3/8, and 4/8. 4/8 is the same as 1/2. And I'm going to plug these values in the calculator. Going here, and taking out that function and plugging in instead e to the negative x squared plus braces. Alright. Window goes from 0 to 1/2. The y values 0 to 1. Okay. Nice. Go to my table. I'm going to plug in 0, 1/2, 1/4, 3/8, and 1/2. Wait, why is that 1/2? No, it should be 1/8. So 1/8 is 0.9845. This is 1 because e to the 0 is 1. This one is 0.93941. 3/8 is 0.86882. And 1/2, 0.7788. Okay, so I've got these values, and we want the left Riemann sum. So we're going to use the first 4 and not the last one. And so we're going to have subinterval width was 1/8. 1/8 times 1 plus 0.9845 plus 0.93941 plus 0.8688. And I can stop there. This is which is an overestimate for the integral of f of x dx on 0 to 1/2. Okay. We have to find anything else there? No, not with that first one. Ooh, now we want the average value. Okay, not average rate of change. Remember, average rate of change on A to B. Average rate of change in f of x on A to B is f of b minus f of a over b minus a. And this should very much not be confused with average value of f on A to B. So what's my average value of f on A to B? That's 1 over b minus a. Integral A to B of f of x dx. Okay, this f is that function. This f is that function. But even though it looks like I should be able to set that equal to that, no, these need to be the antiderivative of this, not the same as this. So there's my average value formula. We're looking at going from 0 to 1/2, integral 0 to 1/2 of e to the minus x squared dx. No, it's not a u sub. I don't even really want to try it by parts. So I think what I'm going to do instead is pull out my calculator. So we want the integral of that function in y1. So math integrate y1 comma x comma 0 comma 1/2. Okay, so this number turns out to be 0.4612810064. But don't lose that 1 over 1/2, which is the same as 2 times that. Again, times 2, and I get 0.92256201228. And that's the average value. Well, that's really interesting, isn't it? Because when we think about this problem, we're looking at, oh, and I know that this is 0, 1, but, we're heading towards 0 as x heads to infinity, but we're only looking until we get to 1/2. And the y value here, as I recall from my table, at 1/2, we had 0.7788, I believe. Okay, and so the average of all of these heights, from a height of 0.7788 to a height of 1, the average of all those heights is 0.923. Okay, so there's station 7. Copy that and paste it here. Station 8. Station 8 says find the displacement and the distance traveled by the happy flying pig. Ooh, I have a happy flying pig. If its acceleration is given by a of t. Well, isn't that interesting? They tell me that a of t, and we remember that that's the same as dv dt, equals 6 sine t. Okay, so let's do separation of variables. 6 sine t dt, and let's integrate to get v equals negative 6 cosine t plus c. Now we are given an initial condition, v of 0 equals negative 9. And so I'm going to take that negative 9 and plug it in here, and that 0 and plug it in there. Negative 9 equals negative 6. Cosine of 0 is 1. And so I see that negative 3 is what c is. So my velocity function, minus 6 cosine t minus 3. All right. And what do we want? We want to find the displacement. Well, I know the displacement is going to be s of pi minus s of 0. That's position, which is in fact the antiderivative of velocity. T from 0 to pi. Okay, so if I integrate this function from 0 to pi, I'll know the displacement. Okay, so let's use that. Let's say the integral from 0 to pi of minus 6 cosine t minus 3 dt. So the antiderivative here will be negative 6 sine t, and the antiderivative here will be minus 3t, going from 0 to pi. Okay, so if I plug a pi in, the sine of pi is the y value of pi, that's 0, times negative 6 is 0, and here we have minus 3 pi. 0 minus 3 pi, and I want to subtract what happens when I plug in a 0. Sine of 0 is 0, and 3 times 0 is 0. Okay, and so I end up with negative 3 pi is the displacement. That's equal to s of pi minus s of 0. And these are in kilometers. Okay. Acceleration given by, there's our v sub o. Find the displacement for the flying pig. Flying pig, 3 kilometers to the left. This would be station 9. Who's station 9? That's graphy. And there's a table here. Oh. Move, you do move. Oh, isn't this interesting? Yeah, I like this problem a lot. I'm glad I have this here. So we're given a graph of G prime. G prime is given here. It looks like trapezoid until we get to here. And this is 4. And that's 5. So 3. This is 1. Yeah. And I don't know where that is. I suspect because this is positive 20 and this is negative 20. At this point it has to be 3.5. Okay, I'm not sure what I'm doing. They do also tell me here that g of 0 equals 5. And we're asked to fill in this table. And it's got x values and g of x values. 0, 1, 2, 3, 4, 5. But we know that g of 0 is 5. Good. Okay. Now what? Well, how do I find g of 1? G of 1? Well, remember, if we integrate from 0 to x, g prime dt, we integrate this curve until we get to a second point. We know that that's equal to g of x minus g of 0. So our g of x function is going to be g of 0 plus the integral from 0 to x of g prime dx. Okay, so if I integrate, I'm using this formula, and I want to know g of 1. Well, g of 1 is going to be g of 0 plus the integral from 0 to 1 of g prime. Well, I know the integral from 0 to 1 of g prime is just the area of this triangle. So that's going to be 5. Sorry, not general form, specific form. I know that's going to be 5 plus, that's a triangle, 1/2 base of 1, height of 20. That's going to be 10 plus 5, or 15. And if I want to do g of 2, then I'm still going to go from 0 to 2. And if I go 0 to 2, I notice that actually I don't have to start all the way back at 0. I would say that g of 2 is equal not to g of 0, but to g of 1 plus the integral from 1 to 2 of g prime. Well, from 1 to 2 is just this, with a base width of 1 and a height of 20. So g of 1 was 15, and the integral from 1 to 2 should give us 1 times 20, and that'll be 35. Okay, g of 3 well, I'm thinking now I could think about that as g of 3 equals g of 2 plus the integral from 2 to 3 of g prime dt. Well, g of 2 is 35, and to integrate from 0 to 3, from 2 to 3, it's just me adding another one of those boxes. And we found out that those boxes had a width of 1 and a height of 20. And so I end up with 55 here. Okay. G of 4. G of 4. Well, so here's what I noticed. I noticed that I could write this as the g of 3 plus the integral from 3 to 4 of g of x dx. Or I guess it's g prime. All right, so that's a little uncomfortable though, because I got this triangle and I got this triangle. And you might want to figure this out as two separate triangles. If we do this as two separate triangles, we've got 1/2 4 minus 3 times, what's the height? Height here is 20. And then I have this triangle. Oh, it's not that. It's 4 minus 3.5. Yeah, I really feel like I should check that out. I mean, I know because this is 20 and this is negative 20, and we're going a distance of 1. That must be that. But if you're not sure, by all means, this other thing, okay? Where you write the equation of that line, and then set that line equation equal to 0, and solve for 2, okay? So that's this one. But now I need this one, which is plus, going to be below the x-axis, so it's minus 1/2 4 minus 3.5 minus this one, since it's here, is 3.5 minus 3. Okay, times the height of negative 20. All right, so this is going to be 1/2 times 1/2 times 20. And over here, we're going to have 1/2 times 1/2 times negative 20. That's interesting. Oh, this minus is because I was below, so I don't want to use that minus twice. Let's do that. There we go. And so that's going to be negative 5. Negative 5 plus 5 is 0. We understand that graphically because this and this are the same area and therefore undo each other. So I end up with the same answer over here for 4. Finally, number 5, g of 5 is going to be g of 4 plus the integral from 4 to 5 of g prime dt. Well, g of 4 is 55, and the integral of this graph from 4 to 5. Well, from 4 to 5, we just have a big old rectangle whose length is 1 and whose height is minus 20. So I want minus 20 times 1 is positive 35 for g of 5. All right. Yeah, that's station 9. Change that one over here. Move this little table over there. Okay, these are ready. Now, station 10. A particle moves along a horizontal path. Its velocity for t greater than 0 is given by v of t equals t over 4 minus 1 over t, and these are in meters per second. At t equal to 1, the particle is 3 units to the left of the origin, so x of 1 is negative 3. All right, part A. Find any time when the particle changes direction. Well, particle changes direction when the velocity goes to 0 and I have a sign change. So let's take a look. When is this equal to 0? All right, let's start by making a common denominator. In fact, let's be even smarter. Since we're solving an equation, let's just multiply everything by 4t. 0 times 4t, still 0. If I distribute this 4t here, the 4's cancel, and I'm left with t times t squared, minus, and when I multiply this 4t here, the t's cancel, and I get minus 4. Oh, well, look at that. We get t equals plus and minus 2. However, remember how the direction said greater than or equal to 0? Yep, don't want to lose any points for that. Okay, so t equals 2. 2, that's time equal to 0. And this is v. So times when the particle changes direction. Well, if I plug a 1 in here, I'm going to have 1/4 minus 1. That is distinctly negative. If I plug something here like a 4, okay, 4 over 4 is 1. 1 minus a negative 1/4. Where's that the last part? I think it's 4, negative 1/4. And that's definitely positive. So particle changes direction at t equals 2, where v equals 0 and changes sign. Okay, that's part A. Part B, find the displacement from 1 to 5. Okay, 1 to 5. So, they said displacement. So remember, to find displacement, x of 5 minus x of 1 is the integral from 1 to 5 of v of t dt. Okay, so, which means I need to evaluate this, and I know that. Okay, so what's my antiderivative here? The antiderivative would be t squared over 8, because when I brought that down, there would be some cancel, I'd be left with that. And whose derivative are you? You are ln's derivative. Now, I want to evaluate u from 1 to 5. Don't forget, I have to add x of 1 to both sides. So, plus -3. All right, 25 eighths. 25 eighths minus 5 minus -3 plus 1 eighth and minus the ln of 1. And the ln of 1 is 0. So, are there any like terms to combine? Not really in the helpful place. Well, maybe. That's going to be -1/8 plus 25 eighths is going to be 24 eighths, which is 3. -3 plus 3, that's 0. And then over here, I have minus and minus is plus 3. So, 3 minus ln of 5. That would be my answer for the displacement asked for in part B. Part C, the total distance traveled on 1 to 5. Well, again, I see that word total, and it makes me think, it really does make me think, that v is going to be changing sign at that point, or at some point on 1 to 5. And I'm going to need a couple of integrals here. So, let's, all right, so let's set v equal to 0. Oh, didn't we come up with v is equal to 0 and I multiply by t squared minus 4. And so we've got t equals 2. Okay, so here's v, here's 0, here's 2, and we're looking for total distance traveled. And when we plugged in a 1, we had a minus, and then we had a plus when we plugged in a 4. Okay, so what does that tell me? Well, it tells me that this is negative from 0 to 2. So I want minus the integral from 0 to 2 of v of t dt plus the integral from 2 to 4 of v of t dt. Great. So this one's being subtracted because v is negative on that integral. And this is being added because v is positive on that integral. Okay, and I need to find these values. I think I'm going to skip that because I really don't think you need my help with that. But no, you're not done yet. And yes, you have to evaluate each of these integrals using this v of t and move on. Okay. 2. The rate at which Coumadin, a blood thinner, your parents may be taking, decreases in the body by an amount proportional to the amount of Coumadin in your body. Okay. But wait a second. I didn't finish the last 2 problems in Station 10, or the last 2 parts of problem 1 on Station 10. So, acceleration. Well, if v is t over 4 minus 1 over t. It might be easier if I wrote that as 1/4 t minus t to the minus 1 for the purposes of finding a of t, also known as v prime. And so the derivative here is 1/4, and I bring on that minus 1, minus 6 minus 6 plus t to the minus 2. So there is the acceleration function, and it says here, find the acceleration for any times when the particle is at rest. Well, we determined particle is at rest when v equals 0. Well, we said that only happened at time equal to 2. And so they want to know the acceleration at any moment when velocity is 0. Well, that moment is 2, so I need to find a of 2. 1/4 plus 1 over 2 squared. Oh, 1/4 plus 1/4 is 2/4, or 1/2. Okay, and then finally, part E. We're looking for x of 5. Okay, so x of 5 minus x of 1 equals the integral from 1 to 5 of t over 4 minus 1 over t dt. Okay, this is the thing we're looking for. They tell us that this amount is minus 3. So minus or plus 3. Okay. Integral from 1 to 4. 1 to 5. This is actually our answer to part B, which I don't remember. So I'm going to take that answer from part B and subtract 3 from that answer. I think because this video is already at 1 hour and 23 minutes, I'm going to scooch along and let you compute that again, and then finally subtract a 3 from it. Great test question, though. I definitely expect to see that. Okay, Station 10, problem number 2. Coumadin, the rate at which dc dt is proportional to the amount of Coumadin in your body. When will only 8% of the original amount of humans generally process half the drug in 40 hours? Okay, so we know that it's kind of like a half-life problem, where C is about E to the KT, and how do I know that? Because I kind of solved this already, but let's solve this differential equation. Multiply both sides by dt, and dt. Also divide both sides by c. ln of c is kt plus. Ooh, I don't like that. Too many variables in the soup. Okay. And then I'm going to do this exponentiating. And I'm going to have c equals plus or minus e to the d times e to the kt. And let's say that plus or minus e to the d equals c sub o. And we can say c equals c sub o e to the kt. All right, so there's my model. And they want to know when only 8% of the original amount maintains if we generally process half of the drug in 40 hours. So C is half of C sub O when T equals 40. Okay, so I'm going to replace this with that. 1/2 C sub O, C sub O, e to the k times 40. Divide by c sub o. Take the ln of both sides. Yes, you do need to bring that down. And so we get our 40k. So k is ln of 1/2 over 40. Okay, I have a value. I have a model too, don't I? Yeah, there it is. So we know that c equals c sub o. C sub o? No, c sub o e to the 1/2 over 40t. Okay, and we're told 8% remains. Well, remember our definition of percent is c over c sub o. So if I divide both sides by c sub o, I'll get c over c sub o, and that'll be percent. We want to know that 0.08 equals e to the ln of 1/2 over t times, I don't know when because I'm trying to find out when, right? Yeah. Okay, so let's take the ln of both sides. It's ln of 1/2 over 40. Okay, multiply both sides by 40, divide by ln of 1/2. So ln of 0.08 divided by ln of 0.5 and multiplied by 40. And I get t equals 145.754. And I think these are hours. Yep, time units are in hours. When will only 8% remain after 145.754 hours? Excellent. Okay. 10 is done. We're up to 11. 11. Car travels at 88 feet per second with constant deceleration and stops at 200 feet. This is cars initially moving at 88 feet per second. And stop. Let's see. Thirteen. Okay. I think I need a quick break. So sadly, there's going to be a part 2 for these last 3 problems. Grrr.